November 1944. The cold waters off the coast of England had claimed another victim. A German submarine, designated as a Type 7C U-boat, had been forced to the surface after a relentless depth-charge attack. The crew abandoned ship, hatches were deliberately opened to prevent capture, and the vessel began its descent to the seafloor. But this time, something different would happen. British salvage teams were already on their way. This wasn't just another sunken enemy vessel to be left at the bottom of the sea. This was an intelligence opportunity that could change everything the Royal Navy thought they knew about their adversary's most dangerous weapon. The submarine came to rest at a depth of only 40 feet, shallow enough for divers to reach, shallow enough for salvage operations. The crew had escaped, but they left behind something far more valuable than code books or charts. They left behind the boat itself. Within days, British salvage teams raised the U-boat, pumped it out, and towed it to England. It was a prize of war, but not for the reasons anyone initially expected. The submarine was transported to a facility in Teddington, where a team of metallurgists waited. These weren't ordinary engineers. They were specialists in material science, men who understood metal at the molecular level. Their leader was a man whose findings would reveal one of the most devastating secrets of the German submarine fleet. Pieces of the hull were cut away, prepared for testing, subjected to analysis that would expose a fatal flaw hidden within the steel itself. If you're finding this story fascinating, please take a moment to click the like button and subscribe to our channel. Your support helps us bring more untold stories from World War II to light. And leave a comment below telling us what aspect of submarine warfare interests you most. Intelligence reports had always claimed that Type 7 U-boats could dive safely to 200 meters. German technical manuals captured in France specified hull steel with tensile strength sufficient to withstand pressure at that depth. The calculations were clear. The design was sound. On paper, these submarines should easily meet those specifications. They should withstand the crushing force of water at 200 meters depth. They should perform exactly as designed. But the steel samples being tested told a different story. The metallurgists subjected the hull steel to pressure tests, simulating the forces a submarine would encounter at depth. The results were shocking. The steel that should have been capable of withstanding pressure at depths exceeding 250 meters was failing catastrophically at only 140 meters. This wasn't a minor deviation from specifications. This was a fundamental failure of the material itself. The hull design had included a safety factor. Test depth was rated at 200 meters. Crush depth, the theoretical maximum before catastrophic failure, was calculated at 280 meters. German submarine commanders knew these numbers. They had memorized them. They trusted them with their lives and the lives of their crews. They knew that diving below 200 meters was dangerous. Below 280 meters was unthinkable. The boat would implode. The pressure hull would collapse. Everyone inside would perish instantly. But 200 meters was supposed to be safe. It was supposed to be within design limits. It was supposed to be survivable. The test results revealed something terrifying. Every time a U-boat dove to 190 meters to escape depth charges, it was gambling with steel that might fail without warning. Every deep dive was potentially the last. The crews had no way of knowing. The steel looked normal. It performed normally under most conditions. But under extreme pressure, deep underwater, it failed suddenly and catastrophically. The metallurgists discovered the cause: molybdenum deficiency. The alloy was supposed to contain specific amounts of molybdenum, a metal that provides crucial strength and resistance to stress. But Germany was experiencing severe shortages of strategic materials. The war economy was struggling, resources were scarce, and somewhere in the supply chain, someone had made a decision. Perhaps it was intentional cost-cutting. Perhaps it was desperation. Perhaps it was simply the inevitable result of a nation running out of everything it needed to continue fighting. Whatever the reason, the steel being used in U-boat hulls was substandard. It was inadequate. It was fatal. The implications were staggering. How many submarines had been lost? How many crews had perished, not from enemy action, but from their own equipment failing beneath them? The hull steel would reach its stress limit during a deep dive. The metal would shatter. The submarine would implode. Water would rush in faster than the human eye could perceive. The pressure wave would end lives in a fraction of a second. The boat would sink to the bottom as scattered wreckage. No survivors, no distress signal. Just gone. Vanished from the face of the earth as if they had never existed. The lead metallurgist compiled his findings into a preliminary report dated November 15, 1944. The document was marked urgent. It detailed the test methodology, the results, the analysis of the molybdenum deficiency, and the conclusions. Those conclusions were devastating. German U-boats could not safely dive to their rated depth. The risk of catastrophic hull failure was significant and increasing with every dive. The steel was not just inadequate when new, it was subject to metal fatigue. Each deep dive stressed the hull. Each stress cycle weakened the molecular structure. After approximately 20 deep dives, the cumulative damage would be severe enough that even diving to moderate depths could trigger sudden failure. The report went to Admiral Sir Max Horton, Commander-in-Chief of Western Approaches. Horton had been fighting U-boats for 4 years. He had seen the Atlantic turned into a graveyard. He had sent thousands of men to hunt submarines in some of the most hostile waters on Earth. He understood the implications immediately. If German submarines could not safely dive to 200 meters, that changed everything. It changed tactics. It changed strategy. It changed the entire calculus of the Battle of the Atlantic. A meeting was convened. Naval intelligence officers, submarine warfare specialists, and operational commanders gathered to discuss the findings. The questions came rapidly. How many U-boats are affected? Unknown. But probably all vessels built after 1942, when material shortages became critical. How many have been lost due to hull failure rather than direct combat damage? Unknown. Depends on when the steel quality degraded. Possibly hundreds. Can we verify this with other captured boats? Yes. Testing should be conducted on hull samples from every U-boat recovered. The strategic implications were discussed for 2 hours. If U-boats could not dive safely below 180 meters, that meant Allied depth charges set to detonate at 200 meters were pushing German submarines into crushed depth. The standard tactic was to force the submarine deep, then destroy it with explosives. But now it appeared that forcing it deep might be enough. The submarine's own hull would become the weapon. This revelation explained something that had puzzled Allied naval commanders for months. U-boats were disappearing, not from confirmed attacks, not from known minefields. They were simply vanishing. A submarine would be on patrol, maintaining radio contact, reporting its position and status. Then silence. Nothing. The boat would never return to base. No wreckage would be found. No survivors would be rescued. The submarine and everyone aboard would simply cease to exist. Intelligence analysts had attributed these losses to unrecorded attacks, to mines, to mechanical failures. Now there was another explanation. The submarines were imploding. The hulls were failing. The boats were diving to operational depths that should have been safe, and the steel was shattering beneath the pressure. Crews were experiencing sudden catastrophic failure with no warning, no time to react, no possibility of survival. German submarine commanders had noticed something wrong. They reported unusual pressure hull noises at depth, strange creaking sounds, metallic groans that shouldn't have been there. They reported boats that dove deep and never returned. They reported hearing implosions on their hydrophones, the underwater listening devices used to detect enemy ships. The sound of a submarine crushing under pressure is distinctive. A deep grinding crunch, then silence, then nothing, forever. But the German Naval Command had not understood what was happening. They attributed the losses to enemy action. They believed depth charges were finding their mark. They thought their submarines were being destroyed by British and American anti-submarine warfare. They never suspected that their own supply chain, their own material shortages, their own desperate economy was ending the lives of their submariners more effectively than any Allied weapon. The British findings remained classified. They were not shared with the public. They were not announced in press releases. They were operational intelligence used to refine tactics and strategies. Allied anti-submarine forces adjusted their approach. Depth charge patterns were modified. Attack procedures were updated. The goal was to force German submarines deep, to stress their hulls, to exploit this hidden weakness. After the war ended in 1945, the full scope of the tragedy began to emerge. The Admiralty commissioned a comprehensive study. Researchers reviewed all U-boat losses, compared loss locations to water depth, analyzed German casualty records, and interviewed survivors. The conclusions were sobering. Of the 200 U-boats lost in circumstances suggesting possible structural failure, approximately 127 were lost in deep water following depth charge attacks. These boats probably imploded due to hull failure rather than direct explosive damage. The steel could not withstand the pressure. The crews perished instantly. If the steel had met specifications, many of these submarines might have survived. They might have escaped the attacks. They might have brought their crews home. The report estimated that defective hull steel cost Germany between 127 and 170 submarines. That represented between 3,000 and 4,000 submariners. 3,000 to 4,000 men who trusted their equipment, who believed in their boats, who thought they were dying in combat when in reality they were victims of their own nation's industrial collapse. The number of deep dives a U-boat could safely complete before risking catastrophic failure was estimated at approximately 20. 20 times a submarine could push to near its rated depth, before the accumulated stress damage made the hull dangerously unreliable. Some boats never made it to 20. Some exceeded that number through luck. But 20 became the rough threshold, the invisible limit that submarine commanders didn't know existed. One German submarine commander, Otto Schmidt of U-437, survived the war and later wrote about his experiences. He described a patrol in late 1944 when his boat was attacked by British destroyers. Depth charges detonated all around them. The pressure hull groaned and creaked. Paint flaked off the interior walls. Light fixtures shattered. Men prayed or wept or simply stared in silence. Schmidt ordered the boat deeper, down to 190 meters, trying to escape beneath the attack pattern. The noises from the hull became terrifying, a sound like tearing metal, a grinding that seemed to come from everywhere at once. Schmidt made the decision to surface, to surrender, to save his crew rather than risk going any deeper. Years later, after reading the British reports that were eventually declassified, Schmidt understood how close they had come. His submarine had been on the verge of implosion. The steel had been failing. A few meters deeper, and U-437 would have been crushed. Schmidt and his crew would have perished. They survived by luck, by surfacing before the hull collapsed. Schmidt wrote that learning the truth was disturbing. Knowing that his boat could have imploded at any moment, that he and his crew were riding in what could only be described as inadequate equipment made of substandard steel, that they trusted their lives to metal that Germany knew was not up to specification, it haunted him for the rest of his life. The metallurgical examination of captured U-boats revealed other problems beyond the molybdenum deficiency. Welding quality was inconsistent. Some seams showed proper fusion and strength. Others were poorly executed, containing voids and weak points. The quality control that had characterized early German submarine construction had deteriorated as the war progressed. Experienced welders were conscripted for other duties or lost in combat. Replacements were hastily trained, standards slipped, inspections became less rigorous. The pressure to produce more submarines faster overrode the imperative to produce them properly. Riveting, used in some hull sections, showed similar degradation in quality. Rivets were improperly set, not fully seated, or made from inferior materials. Each imperfect rivet was a potential failure point. Under extreme pressure, these weak spots could initiate catastrophic hull breaches. The submarine might survive 1 deep dive, 2, 10, but eventually the weakest point would give way. And once the hull was breached at depth, even by a small crack, the pressure differential would tear the submarine apart in seconds. The British divers who first inspected the captured U-boat had no idea what they would ultimately discover. They were looking for intelligence material, for equipment to study, for tactical information. What they found instead was evidence of a systemic failure that had claimed thousands of lives. The divers examined the hull, noted the construction techniques, documented the materials. Their initial reports were technical and straightforward. But those reports set in motion the chain of investigation that revealed one of World War II's most tragic secrets. Diving on a U-boat at 40 feet depth was relatively straightforward for trained naval divers. The visibility was poor, as it usually was in British coastal waters. The water was cold, requiring proper exposure protection. The submarine itself was an eerie sight, a war machine lying silent on the seafloor, still dangerous even in defeat. Unexploded torpedoes might still be aboard. Batteries could leak toxic chemicals. Fuel tanks could rupture. The divers worked carefully, methodically, documenting everything they found. The salvage operation was a significant undertaking. Heavy lift vessels were brought in, chains were passed under the hull. Pumps were prepared to displace the water inside the submarine. Slowly, over the course of several days, the U-boat was raised. Water poured from every opening as it breached the surface. It was towed to port, placed in dry dock, and systematically examined. Engineers crawled through every compartment. They photographed everything. They removed equipment for study. They took samples of the hull steel for metallurgical analysis. That analysis would prove to be the most important work of all. The samples were sent to Teddington, to the laboratory where materials testing could be conducted under controlled conditions. This was where the truth would be discovered. The testing process involved subjecting steel samples to increasing pressure while monitoring their structural response. The test apparatus could simulate the water pressure at various depths. Gauges measured the point at which the metal began to deform. More importantly, they measured the point at which the metal failed catastrophically. That failure point should have been well beyond the submarine's rated diving depth. Instead, it was far below it. The metallurgists also examined the steel's crystalline structure using microscopy. They analyzed its chemical composition using spectroscopy. They conducted hardness tests, tensile strength tests, and fatigue tests. Every analysis confirmed the same conclusion. The steel was substandard. It lacked crucial alloying elements. Its grain structure was inconsistent. Its performance under stress was inadequate for the application. When the test results were compiled and analyzed, the full picture emerged. This wasn't a one-time manufacturing defect. This wasn't a single bad batch of steel. This was systematic, widespread, and ongoing. Germany's industrial base was failing. The submarine fleet was being constructed from inferior materials because superior materials were no longer available in sufficient quantities. Every U-boat launched after a certain date was potentially affected. Every crew was potentially at risk. The revelation raised ethical questions that were discussed at the highest levels of British naval command. Should this information be made public? Should it be shared with neutral nations? Should it be used as propaganda to demoralize German submariners? Ultimately, the decision was made to keep it classified. It was more valuable as operational intelligence than as propaganda. British anti-submarine forces could exploit this weakness more effectively if the Germans didn't know it had been discovered. But there was another consideration. Revealing the defect might prompt Germany to correct it. If German Naval Command understood that their submarine hulls were failing, they might take steps to address the problem. They might source better steel, even if it meant diverting resources from other programs. They might improve quality control. They might save the lives of their submariners, and that was something the Allies did not want. Every U-boat that imploded from hull failure was one less submarine attacking convoys, sinking merchant ships, taking the lives of Allied sailors. This was the cold calculus of war. Information that could save lives was withheld because those lives belonged to the enemy. The British had discovered that German submarines were vulnerable in a way their crews didn't understand. That knowledge was a weapon, and it would be used. The testing program expanded. Every captured U-boat was examined. Hull samples were taken from multiple locations on each vessel. The data accumulated. Patterns emerged. Submarines built earlier in the war showed better steel quality. Those built in 1943 and 1944 showed progressively worse quality. The correlation was clear. As Germany's war economy deteriorated, so did the integrity of their submarine fleet. Some captured U-boats showed evidence of previous hull damage that had been repaired. Cracks had been welded over, dented sections had been hammered back into shape. These repairs were often poorly executed, creating new weak points. German shipyards were overwhelmed with work. Damaged submarines needed to be returned to service as quickly as possible. Proper repair procedures were shortened or skipped entirely. The pressure to maintain operational fleet strength overrode engineering best practices. One particularly revealing case involved a U-boat that had been captured relatively intact. The submarine's logbook was recovered, providing a detailed record of its patrols and diving operations. British analysts counted the number of times the boat had dived below 150 meters. The total was 23. On the 24th patrol, the submarine had been forced to dive deep to escape an attack. It had surfaced shortly afterward, with severe hull damage, water flooding into multiple compartments. The crew had been forced to abandon ship. The submarine had been scuttled to prevent capture, but Allied forces had salvaged it anyway. Metallurgical examination of that submarine's hull revealed extensive stress fractures. The steel showed clear evidence of fatigue failure. Microscopic cracks had formed and propagated through the material. In several locations, these cracks were dangerously close to causing catastrophic failure. If the submarine had attempted one more deep dive, it likely would have imploded. The crew had been operating on borrowed time, completely unaware of how close they were to sudden ending. This case study was included in the comprehensive report prepared after the war. It became Exhibit A in the analysis of how metal fatigue from repeated deep dives contributed to U-boat losses. The 20 deep dive threshold was an average, not an absolute limit. Some submarines failed sooner, some lasted longer, but the pattern was consistent. Repeated stress cycling of substandard steel led to progressive weakening until catastrophic failure occurred. The human cost of this industrial failure is difficult to fully comprehend. Each submarine carried a crew of approximately 40 to 50 men. They lived in cramped conditions, breathing recycled air, eating preserved food, never seeing sunlight for weeks at a time. They faced enemy attacks, mechanical failures, and the constant psychological stress of knowing they were sealed inside a metal tube hundreds of feet underwater. And unknown to them, they faced another threat, their own hull slowly weakening with each dive until the ocean itself would crush them. Letters from German submariners to their families captured or recovered after the war sometimes mentioned concerns about their boats. One sailor wrote, "We dove deep yesterday to escape the destroyers above. The sounds from the hull were frightening. Several of the men thought we were done for, but the boat held together. We surfaced after dark and continued our patrol. I wonder how much more she can take. That submarine never returned from its next patrol. It was listed as lost with all hands. Cause unknown. Now we know the hull probably failed during another deep dive. The boat imploded. The crew had no chance. Another submariner wrote, "Our boat makes noises it never made before. The chief engineer says it's normal, just the hull adjusting to pressure. But some of the older hands aren't so sure. They talk about boats that went down and never came back up. They wonder if something is wrong with the new steel. But what can we do? We have our orders. We dive when we must." That letter was found in the personal effects of a sailor whose submarine disappeared in the North Atlantic in 1944. The boat was never found. It is listed in German records as lost to unknown causes. The British report identified it as a probable hull failure casualty. The psychological impact on survivors who later learned the truth was significant. They had trusted their boats. They had believed in German engineering. They had thought that if they followed procedures and maintained their equipment, they would be as safe as any submariner could be in wartime. Learning that their hulls were defective, that their safety margins were illusory, that they had been diving in equipment that could fail without warning, it was a betrayal. Not by their commanders or their crews, but by the industrial system that was supposed to supply them with reliable equipment. Some survivors experienced what we would now call survivor's guilt. Why did their boat survive when so many others didn't? Was it luck? Better quality steel in their particular vessel? Fewer deep dives? They would never know for certain. They could only be grateful they had survived and mourn those who hadn't. The story of defective U-boat hull steel is ultimately a story about the limits of industrial warfare. Germany was fighting a multi-front war against opponents with superior resources. The German economy was under strain from the beginning and progressively deteriorated as the war continued. Strategic materials became scarce. Quality control suffered. Corners were cut, and men paid with their lives for decisions made in distant offices and factories. This wasn't unique to Germany. Every nation involved in World War II faced similar pressures. Equipment was rushed into production. Standards were compromised, quality varied. But the consequences were particularly severe for submarine crews because they operated in an environment that was inherently unforgiving. A tank crew in a defective vehicle might survive. An aircraft crew in a flawed plane might make an emergency landing. But a submarine crew in a vessel with a defective hull had no second chances. When the hull failed at depth, everyone aboard perished instantly. The British investigation into U-boat hull steel remained classified for many years after the war. When portions were finally declassified and released to researchers, they provided crucial insights into submarine warfare and material science. The findings contributed to improved standards for submarine construction worldwide. Modern submarines use steel with carefully controlled composition and strict quality control at every stage of production. Welding is performed by certified specialists using standardized procedures. Hull integrity is verified through rigorous testing before a submarine enters service. Today's submarine crews dive deeper and stay submerged longer than World War II submariners could have imagined. They do so with confidence in their vessels because the lessons of the past have been learned and applied. The tragedy of the U-boat fleet with its defective hulls helped ensure that future submarine crews would not face the same hidden threat. The discovery made by British divers and metallurgists in 1944 was a turning point in submarine warfare. It revealed that the enemy's most dangerous weapon had a fatal weakness that even the enemy didn't fully understand. It demonstrated that industrial capacity and material quality were as important as tactics and courage in determining the outcome of naval combat. And it showed that sometimes the greatest threat comes not from the opponent across the battlefield, but from failures in one's own supply chain. The U-boat crews who perished due to hull failure were skilled sailors, brave men doing their duty as they understood it. They deserved equipment that would protect them as well as humanly possible. They didn't get it. They got substandard steel, inadequate quality control, and hulls that failed after only 20 deep dives. They paid the ultimate price for their nation's industrial shortcomings. Their story is a reminder that in war, as in all things, the details matter. The composition of steel matters. The quality of welding matters. The consistency of manufacturing matters. When those details are wrong, people perish. The submarine that British divers inspected in 1944, the one that revealed this fatal secret, has long since been scrapped. The hull samples tested at Teddington are presumably archived somewhere in British military records or have been destroyed. But the knowledge gained from that investigation, the understanding of how material defects can doom military equipment, and the men who depend on it, that knowledge remains relevant. It informs decisions about military procurement, about quality assurance, about the importance of maintaining industrial standards even under the pressures of wartime production. The ocean floor still holds the remains of U-boats that imploded due to hull failure. These wrecks are war graves, final resting places for crews who never knew what happened to them. In an instant, they went from living, breathing, thinking human beings to victims of catastrophic structural failure. Their submarines are scattered across the seabed, twisted metal and broken equipment, marking where the ocean's pressure overwhelmed defective steel. Some of these wrecks have been located by modern researchers using advanced sonar and deep-diving submersibles. The wreckage patterns are consistent with implosion, hull sections crushed inward, equipment compressed, debris scattered over a wide area. These physical findings confirm what the British discovered in 1944. The submarines didn't sink because of enemy weapons. They imploded because their hulls couldn't withstand the pressure. The ocean itself became the weapon, exploiting the weakness in the steel. For the families of German submariners lost during World War II, the revelation about defective hull steel brought a mix of emotions. Some found a kind of closure, understanding finally what had happened to their loved ones. Others felt anger that such a preventable cause had claimed so many lives. Still others simply mourned, knowing that, whether death came from an enemy depth charge or from defective steel, their fathers, brothers, and sons were not coming home. The legacy of this discovery extends beyond military history. It has implications for any industry where material quality is critical to safety. Aerospace engineering, bridge construction, pressure vessel manufacturing, all learned from the U-boat hull failure analysis. The importance of material specifications, of quality control, of testing and verification. These lessons have been applied across multiple fields. Lives have been saved because the mistakes that doomed U-boat crews are now better understood and actively prevented. If you've stayed with us through this detailed exploration of how defective steel doomed German submarines, please consider leaving a comment sharing your thoughts. And don't forget to subscribe to our channel for more in-depth World War II stories that reveal the hidden details behind major events. The story of British divers inspecting a captured U-boat and discovering its hull was fatigued after only 20 deep dives is ultimately a story about the intersection of engineering, warfare, and human tragedy. It's about how industrial decisions made far from the front lines determined who lived and who perished. It's about the courage of submarine crews who faced known dangers while being completely unaware of a hidden threat that could end them in an instant. And it's about how knowledge gained from examining enemy equipment can reveal weaknesses that change the course of a conflict. The metal that should have protected those submariners failed them. The industrial system that should have ensured quality control failed them. And the result was that hundreds of submarines and thousands of men were lost, not to enemy action, but to their own equipment's inadequacy. It remains one of World War II's most tragic examples of how the home front's failures can have deadly consequences on the fighting front. The ocean claimed those submarines and their crews, but the real cause of their loss was hidden in the molecular structure of defective steel, a weakness that took British divers and metallurgists to reveal, and a weakness that Germany's submarine force paid for with thousands of lives.